All right. So I'll begin here. So I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for these students. Just pray you help us today to understand this material and be with the students over the break. Help them not to get into any mischief. Amen. Okay, so especially Sharon. Mischief. Yes. Okay, so I want to take a second here back just to, you proved a chain rule for a holomorphic function. You proved that if you have, how's it go? Oh man, I can't remember the way to say it. Curses. It's one of your homework problems. ddt of f of z of t, if z of t is like the if z of t is like a path in the complex plane, right? And it's a differentiable path, and f is a holomorphic function close to this path, then we had this wonderful chain rule that simply said that this is df dz times dz dt, where that's a complex multiplication. That's just a fantastic, so the more general thing over Rn is something like this: f of r of t, right, is equal to the gradient of f at r of t, dotted with the r dt. So that's the chain rule of multivariate calculus. This is the specialization in the complex setting. I mean, that dot product is replaced with this complex multiplication. It's a wonderful, wonderful theorem. So let's see here. Like, for example, ddt of e to the lambda t is equal to what? So this is the composition of what? I mean, this is the composition of f of z is equal to e to the z, which we know is holomorphic, right? And also the z of t is what? Lambda t. And here lambda could be a complex number, right? So this chain rule then immediately tells me that this is lambda e to the lambda t. For complex lambda, which is pretty cool, right? And here's an application of why it's so interesting. So if I take the integral of e to the lambda t dt, how does that work? So this is the integral of a complex valued function of a real variable. So this is just a vector of integrals if we were to write that in real and imaginary notation. However, it's also the case that it's just 1 over lambda e to the lambda t plus some constant, right? And the reason for that is simple. If you differentiate the right-hand side, you get back to the integrand, right? But what does this mean? If you unwrap this, if you unfoil this in terms of its real notation, it's really fantastic what this is. If lambda is equal to alpha plus I beta, where alpha and beta are real, then e to the lambda t is e to the alpha t cosine beta t plus I e to the alpha t sine beta t, right? So to integrate e to the lambda t dt, you see that's to integrate the integral of e to the alpha t cosine beta t dt plus I times the integral of e to the alpha t sine beta t dt. And apparently that's equal to 1 over lambda e to the lambda t plus some constant, right? But continuing here, over here, what is that? That is 1 over alpha plus I beta, right? Oh, yeah. Sorry, my. Thank you. All right. You want to do it, Sharon? Oh, you're going to leave it to, okay. I would say Lauren, but that would be wrong. Lorenzo. Lauren from zoology, so it's clear. All right, so we don't like that. To make this prettier, we do what? We multiply by alpha minus I beta over alpha minus I beta, right? To make it into Cartesian form. And then, of course, the e to the lambda t is, well, e to the alpha t cosine beta t plus I e to the alpha t sine beta t. Okay, so expand this and collect the real and imaginary parts. I've got alpha over, I've got 1 over alpha squared plus beta squared, alpha, e to the alpha, and I've got an e to the alpha t everywhere, so I'll factor that out, e to the alpha t. So I've got alpha, e to the alpha t over alpha squared plus beta squared, and then I got myself an alpha cosine beta t, and then let's see, I times minus I times I gives me minus I squared, which is plus beta sine beta t. Those are the real terms, plus I e to the alpha t over alpha squared plus beta squared. And what are the imaginary terms? Well, imaginary terms are, I got myself an alpha and a sine, so I've got alpha sine beta t. And then, of course, I've also got I've got the minus beta cosine, so minus beta cosine beta t. So the bus drivers already think they're on break, right?
Convo let out at 12:02.
Convo let out at 12:02. Hey.
Convo let out at 12:02.
Hey. I thought the reason we had a longer convo was so that this wouldn't happen. Like.
Well, Louis Giglio decided we needed to have 3 worship songs at the end of convo. Because
Three?
we're in church.
3 worship songs at the end of convo. Well, okay. Well,
No, and I was sitting beside my RA.
the good news is all I'm doing right now is showing you a way to do calculus 2 in a sneaky way. So you haven't missed anything theoretical, complex analysis yet, Malia.
Yeah, we all went to Convo too. We just wanted to be here on time.
Oh, okay.
We're off campus.
Okay, guys, so what was the effort required to do the integration? The effort required to do this integration is over here, pretty much. I mean, that's the integral at the level of complex notation. But when you examine what the import of that is, the content of that is, in terms of real integration, we have just shown, equating real and imaginary parts, that the integral of e to the alpha t cosine beta t is this. And at the same time, in the same calculation, we have also shown that the integral of e to the alpha t sine beta t dt is this, stripping off the I. How did you do these in calculus 2? Do you remember?
I think it required fewer steps.
No.
You use different applications of integration by parts and then
Yes.
solve for L.
These are the ones where you have to integrate by parts twice and it loops back. But when you do that, you only get one of these integrals, not both. I got both integration by. You'd have to do 2 looping integrations. You have to do 4 integration by parts to get all the mathematical content we just got here.
I was just thinking about that guy over there.
Oh, this one?
Like,
Oh, that's just, I mean, that's a guess, right? That's an educated guess based on our knowledge of the chain rule.
okay.
Yeah. So these are the kinds of integrations that we need to be able to do actually to actually flesh out the complex integral. So when you actually get to the explicit calculation of a complex line integral, these are the kinds of calculations that we face. Not this per se, but just generically speaking, a complex valued integral of a real variable. Let me be more explicit here. I thought I threw this out.
Did you even try that one?
You know it's garbage.
We don't know.
Fine, I'll put it over here, behind this chair where it can't hurt anyone. Yes, you are Schindler to erasers. Let's see here. Sorry, it's too obscure a reference. Oh, okay, good. I was going to ask. The question I was going to ask. If I said the phrase "jump the shark," how many people in here know what "jump the shark" means? Show of hands. One.
Is it a math thing?
It's not a math thing. Jump the shark. Who knows what
Then
jump the
how
shark
do they
means?
know it?
Apparently, Nate's knowledge extends beyond mathematics.
Yeah, apparently.
Yeah. All right. How many of you know who Rush Limbaugh is? 1, 2, 3, 4. How many don't know who Rush Limbaugh is? Well, Lauren has to say she knows now, but she has to say no because she understands the. So 1, 2, 3, 4. You don't know either.
I didn't raise my hand that I didn't know.
So you don't know.
Okay.
Interesting. So 50% here. It's 30% of my business calculus. I mean, calculus for life sciences knows who Rush Limbaugh is. I'm curious. Basically,
Call it calculus for life sciences.
calculus for life sciences. Yeah, whatever it is. I think that is actually the title of the course. I was speculating. I have conjectured that in more general classes, my conjecture is that 30% of the people, generally speaking, will know who Rush Limbaugh is. But I'm betting that 50% of the people will know what jump the shark means. I believe this is more commonly known. I could be wrong, though. You're supporting Sprano's conjecture at the moment on the jump the shark. You can explain to them what jump the shark is.
Professors talk about.
Oh, I'm sorry. I digress a little bit. So the integral over gamma of f of z.
You can't lose. It's fun.
Oh, it refers to a later season of Happy Days when the Fonz, like the guy with the leather jacket, was surfing and for some reason he just jumped over a shark. Was there a ramp? I don't know. I haven't seen it. I'm just aware of it. It refers to the episode where Happy Days became ridiculous. And more generally, it's a phrase that's used to reference when a show has reached its absurdity. My brother says, for example, that Hillary Clinton jumped the shark last weekend.
Wait, on that one show she went on?
Yes,
Or
yes,
lookalike?
for example. Okay, so this is u plus I have stuff to cover today. I should behave. Dx plus I am focus. So this is defined as that essentially, and what this actually means, of course, is those dx dy integrals we did before, right? So, I mean, this you could look at it as u dx minus v dy integral plus I times the integral of. I mean, there's a lot of different ways to look at this. Is my point. I'm not sure if this is productive what I'm doing at the moment, but here it is. Now, let me just be more pragmatic. So, example, if I want to look at the integral along the unit circle, all right? So let's C be the unit circle and say dz over z. How does this actually work? I haven't written anything useful up here so far. I mean, the thing that we actually would sometimes do or often do is just this. We do f of the parameterization. So let me just say z of t for the parameterization, and then times dz dt. And that is over the, whatever. So let's say z of t for t1 less than or equal to t less than or equal to t2 parameterizes the curve gamma. At which point you should be like, but I thought you said that gamma curve was a parameterization of a point set. Fine, you got me. Anyway, this is the integral from 0 to 2 pi of what? So what's the parameterization of the unit circle? Counterclockwise oriented unit circle. Right. Okay, yeah, so we do z equals e to the it. I take your theta and make it into a t just because I want to connect with what I wrote there. But yeah, theta would also be cool. Would it be happier if I wrote theta to you guys?
I'd be happier if you wrote a 7.
7. I will not write a 7.
Does Crazy Paul
Joe!
watch these videos?
Oh, no, thankfully Joe is, Crazy Paul has not been watching these videos, as far as I know, but I guess I can't stop him. They are public. Okay, anyway, so what is dz? Well, the way to calculate this, right, you don't really want to go back to this level of stuff if you can. It's better to do these at the level of complex notation if you can hack it. And here we definitely can, because what's dz? I mean, yeah, I e to the it, so like dt, right? So formally, it really amounts to that. So this, I mean, fine, tell you what. So we have I e to the it. If you realize I did a slight bait and switch on you here, right? Because I said you take the curve, you evaluate it, the parameterization, you multiply by the derivative of the parameterization, and then you integrate over dt. But now I'm just saying, well, you just formally calculate dz and plug it in here. You know, well, those are the same thing. And then z is what? Z is e to the it. So, you know, this is actually dz dt times dt, right? So this right here is indeed that term, right? And so, and then what happens is those cancel, right? You get I integral of dt from 0 to 2 pi. What do we get? 2 pi I. Shall we look at another example? I think we shall. Let's see here. Wait a minute. I should check. Do you guys, all your classes, all your other classes today were canceled, right? No. Oh. I thought maybe we could just keep going. Well, abstracts can't, so I can just keep, I have 2 hours today. I could lecture for 2 hours, right? I mean.
Actually 3 hours, because abstract doesn't start till 2:10, so you can go all the way till.
Sorry, fax 488 is still on today, so.
Fax 488 is still on. All right, Sharon. Another example I should work out before I start projecting things. Let's look at the circle, which is basically given by z minus z naught equals to r in the counterclockwise sense. All right, so what would the parameterization of this circle be? You take z naught, and then you add what? R e to the it for 0 less than or equal to t less than or equal to 2 pi, right? So there's a parameterization of the circle. Now I want to calculate the complex line integral of a particular complex function around that circle. And I'm going to be greedy. I'm going to calculate the integral along the circle of, let's say, z minus z naught to the nth power. So what's that? So integral from 0 to 2 pi, right? Apparently that's what? R e to the it raised to the nth power, because z minus z naught is just r e to the it, right? What's dz? Well, dz is r I e to the it dt. Do you have any questions for me, Nathan, about n? What is n?
What is n? An integer?
Yeah, let's say n is an integer. I mean, I suppose we could reasonably let n be a... well, we can't really do that, though, can we? If I wanted to let n be a complex number, I can only do that for a slit complex plane, right? So I can't use... I don't have a z to the complex number power function for the whole complex plane, right? I lose...
It might be fun to talk about them.
Indeed, yes. I mean, we can't help but talk about that. You'll see. So this is what? 0 to 2 pi, r to the n plus 1, right? E to the, and so we have the Moivre's theorem, sorry, e to the it to the n is what? E to the nit. Itnin? Itn? E to the itn? Anyway, the point is that times that gives me n plus 1, right? Times I times t, however you want to write it. dt. And now I think you see the reason I did the example I did at the start of class, is to prepare you. Oh, thank you. Still in the marker. Thank you, thank you, thank you. Now, what value have we already covered over here? What's my previous example? N equals to minus 1, we've already done with z not equal to 0, right? But you can easily see that we can take this example and do it for the circle centered at z naught. And, oh, fine. I mean, I'll just assume n is not equal to 1 here for a second, then I'll show you the n equals to minus 1 case in just a second. So what's the integral? We get I r to the n plus 1, and then we get e to the n plus 1 it divided by n plus 1 times I. That's the antiderivative of this, and I evaluate from 0 to 2 pi. Using the fundamental theorem of calculus part 2 for integrals of real vector valued functions of real variable. Yeah. But this is a complex notation for all that. Fine. So what is that? I mean, it's e to an integer 2 pi multiple of, I have e to the 2 pi times n plus 1 I, and I've got e to the 0. So I've got the upper and lower bounds cancel, and what do you get? Zero. That is good for, just to be clear, e to the 2 pi times n plus 1 I is equal to 1 is equal to e to the 0. So the upper and lower bounds cancel. And n plus 1 is harmless as long as n is not equal to minus 1. Are we good? Yep.
Should you then make an element of like z positive or something? So that n is never equal to -1?
Oh, but that's the thing, no.
No?
This in fact demonstrates that the integral along the circle z minus 3 equal to 7 of 1 over z minus 3 to the 4th power dz, for example, is 0.
Okay.
Despite the fact that there's a divergence. Right? What's a divergence in a complex function? It's kind of the usual thing. It's a place where you have, I want to say it's a place where the function's unbounded. We'll talk about different kinds of what are called singularities of complex functions as we go on. That's one of our long-term goals in here is to classify different kinds of singularities for a complex function. That is what's known as a pole of order 4. This is what's known as a pole of order 1. So there's something different about poles of order 1 and poles of other orders. Like if I have n equals to minus 2, minus 3, minus 4, minus 10, it's always 0. And yet, n equals minus 1. 2 pi I. That's weird, isn't it? I think it's weird. Why is that?
I don't know.
You don't know? Okay. I think it has to do with the connection between the 1 over z function and the log function. All right? Okay, so we can also talk about deformation theorem here, right? What do we have? If we have the integral along loop 1, of omega that's equal to the integral along loop 2 of omega, provided what? They both have to be the same, like both counterclockwise oriented or both clockwise oriented. And what else did we need about the form? What did we need in the region between omega is what? Was the condition?
Closed.
Closed, right. Because if omega was closed, then we can use Green's theorem and the area integral goes to 0. And, well, anyway, through Green's theorem, essentially. So with this, you see, I can calculate what's the integral of dz over z over some loop containing the origin, counterclockwise, right? So if my loop, let's say gamma, so the loop gamma could look like this. Here's 0. This is equal to
Zero.
no,
2 pi i.
2 pi I. Well, yeah, there is something here. In order to use, your what did you say?
I said
2 pi I. Okay. In order to use the deformation theorem, we actually need what? We need this. I do need the unit circle is in here, right? But actually, if you start thinking about it, you can take the unit circle result, right, and shrink it down to like a really, really small loop around 0 itself, right? So, in fact, any simple closed curve which contains the origin has to be 2 pi I, because you can take that example and shrink it down to like a really, really small circle that just contains the origin as well. They all have to give you back 2 pi I. Assuming that you just wrap around the origin once. If the circle wrapped around the origin twice, you get 4 pi I. If it wrapped in the counterclockwise direction, rather than the clockwise direction, you get minus 2 pi I, and so forth. All right, so that's an interesting pair of examples, I think. Now, another fundamental tool we have to work with in the case of the complex integral, is known as the ML theorem. What's the ML theorem say? So first of all, we define the integral of f of z times dz. So we put modulus over dz. What that's defined to be is, I'll just get straight to I have it in terms of Riemann integral in the notes, but I'll just get straight to the point here. It's basically the integral over gamma, of course, say from t1 to t2 of f of gamma of t times the modulus of d gamma dt dt. If you want me to write this in terms of a pair of real integrals that you already know and understand, what this really is the integral along gamma of u ds plus I times the integral along gamma of v ds. These are arc length integrals. It's a complex linear combination of the arc length integral of I'm assuming f is equal to u plus iv, as I usually do. So if you wanted to relate it back to Calc 3, that's what it is, technically. Okay. The modulus of d gamma dt is the speed. So this is really ds dt times dt, right, which is the integral over ds. Anyway, here's the theorem. If the modulus of f of z is less than or equal to m for all z in the curve, and if the length of the, let's say that L is equal to the integral of the modulus of dz over gamma, which is just a silly way of saying that L is the arc length of gamma. Then the following. The modulus of the complex integral of f of z dz is less than or equal to m times L. An example of this. Let's see here. If you look at f of z equal to 1 over z, right? What's the modulus? And let's say on the circle, modulus of z equals to 1, for example. What would m be? You could find m pretty easy here. What's the modulus of f of z? 1 over the modulus of z, right, is equal to 1. So certainly this you can use for m. What's the length? Well, the length is 2 pi for the unit circle, right? I'm thinking about. So, I mean, this is kind of the ultimate success in some sense for this theorem. I mean, the modulus of dz over z is less than or equal to 1 times 2 pi. Well, guess what? That's pretty much spot on, isn't it? I mean, we just calculated it's 2 pi. Let me do a less stupid example. How about this? What if you wanted to find a bound on the integral of dz over z squared minus 6 on the circle, let's say modulus of z equals to r. And to keep things not too annoying, we're going to assume that r is greater than what? R is a real number here. R greater than, what's the square root of 6? I think so it's less than 9, right? So let's let r be greater than 3. That way we know that, it's in there. Okay, so what happens here? We need to find, I'm suggesting then that we should try to bound z squared minus 6, the modulus of 1 over z squared minus 6. So find m. Okay. So we want to look at 1 over the modulus of z squared minus 6, right? Now, if I want to make the fraction have a larger, I'm looking for this inequality, right? I want to make that fraction smaller than what I'm about to write. I need to make the denominator what? Bigger, right? So here's the thing. The modulus of z squared minus 6 is greater than or equal to the modulus, or the absolute value rather, of the modulus of z squared minus the absolute value, well, modulus of 6, absolute value of 6, same thing. That is a consequence of the triangle inequality. So what is this actually equal to here for us? Well, this is equal to r squared minus 6, right? Which is equal to r squared minus 6 in this case because we're assuming that r is greater than 3, so r squared wins over 6. And so you see what I have then is that this is 1 over, r squared minus 6 by this up here. So we can use that as an m, all right? That's m. Es no bueno. And what's L? Two pi r, right? the arc length of that circle is 2 pi r, right? So if we use the ML theorem on this, we have the modulus of the integral over this circle of radius r. I'm assuming it's counterclockwise oriented, but you know, I don't think this problem is really sensitive. If you're looking at the, you know, if you're looking at the modulus of the integral, you can't pick up a sign difference anyway, right? So counterclockwise, clockwise, we wouldn't know the difference. But anyway, so z squared minus 6 is less than or equal to ml, which in this case would be 2 pi r over r squared minus 6 by ML theorem. Which is pretty nice, because if you actually tried to calculate this integral directly, it's kind of a pain, right? So the proof of the ML theorem is on page 80 of my notes. I decided to do examples for you guys today instead of showing you the proof. And that brings us to section 4.2. The proof of the ML theorem is more subtle than you might expect, by the way. Maybe we'll talk about it some other day. But all right, so what are the fundamental theorems of you know, the complex integral? Well, let's see here. If we have integral over gamma, right, of f of z dz, and if f has a primitive, well, excuse me, how does stupid language? I would like to say that f is integrable. All right, that's not in my notes, but I'd like to say that f is integrable on gamma. What that means is that it has a big F, which is a primitive. So say f, big F, is a primitive of f on a domain D if and only if what? F prime of z is equal to f of z for all z and d. That's a definition. So, and I would like to say if this is the case, this means f is integrable on D. I don't believe we use that term anywhere else in the course, so I'd like to start using that as a positive, direct characterization of the function. See, alternatively, I would have to say that little f has a primitive. In other words, it has an antiderivative on all of D. So this is what? Well, suppose that f is integrable. Then this is the integral of, you know, f prime of z dz, right, over gamma. And by the homework you guys just did, this is in fact the integral of what? df over gamma. Remember that I asked you that about snazzy notation? And basically what you worked out there, if you did it, was that f prime of z dz is essentially just df. And we know what the integral of df is. Well, that's an exact form. It's in your face. It's exact, right? And so if gamma is a curve from point A to point B, then of course this is just f of b minus f of a. So I would call this FTC2 for complex analysis. If you have an integrable function, there you go. So I guess it must be the case, right, that the 1 over z function is not integrable on the punctured plane, right? Right? F of z equals to 1 over z is not integrable on the punctured plane. Why? If f of z with f prime of z is equal to 1 over z for all z in the punctured plane, then what would we be able to do? For example, we'd be able to do the integral over the loop. Modulus of z equals to 1 of dz over z is just what? It would be f of starting point, minus f of ending point. Well, sorry, let me use the number 1. See, unit circle, we could say it starts and ends at 1, right? So a equals b equals 1. It's a loop. In other words, if it was exact on the punctured plane, then the integrals around loops in the punctured plane would have to be 0. But we know they're not. We just calculated it this morning. Not just 20 minutes ago. We found out it was 2 pi I for the unit circle. So 1 over z is not integrable on the punctured plane. But where is it integrable? And what is the antiderivative of 1 over z?
Log of z, right?
Right, exactly. d dz of log of z is equal to 1 over z. Where? Where, though? What's the domain of the principal logarithm? The split complex plane. Which one? The standard one. Yeah. This is for z and c minus, as we call it. Right? You get rid of that ray, right? And I could find other antiderivatives, right? I could do like d dz of log sub alpha, say of z, is 1 over z. I could take some other branch of the logarithm. And that could be for like omitting the, say, alpha ray. Losing the alpha ray, right? But there's always some ray that you lose. And that's why there's a 2 pi. And now, what is, what's the difference between what's the difference between 1 over z and anything else? Like, why could we get 0 why did we calculate 0 earlier today? What was the difference with that one? What's the antiderivative? Let n not equal to minus 1. Consider f of z equal to z minus z naught to the n power. What's the antiderivative? This is calculus 1, guys. N plus 1, z minus z naught to the n plus 1, right? If I differentiate that, I get back up there, right? And this right here, so you see f is integrable on c. There is no restriction whatsoever. So if I have an integral along a path, right, of that function, I can just use FTC part 2 and evaluate the antiderivative at the endpoints, right? The subtle point here is that when there's a singularity of the function, right? If there's a singularity of the function inside the loop you're integrating around, it may be that it doesn't integrate to 0. It may be we have this phenomena here, where we pick up some non-trivial contribution. But division by 0 alone is not enough to guarantee that you have 0, that you have non-zero integral. What's the other fundamental theorem of calculus? We usually call it FTC1, right? What was FTC1? In usual calculus, it's d dx of the integral from a to x of f of t dt is f of x. Right? The derivative of an integral with variable bounds is just the integrand again, evaluated at the upper bound. Here, the fundamental theorem of calculus in the complex version involves star-shaped. So you let d be star-shaped. Or you could replace this with simply connected if you wanted to develop that theory. Let d be star-shaped and f of z holomorphic on d. Then f is integrable on d. In other words, f has a primitive, and that's unique up to an additive constant. Moreover, you can say f of z, the antiderivative if you like, is equal to the integral from z naught to z of f of zeta d zeta. Or use w if you like. I mean, whatever. Here, let me use w's. W. There you go. Where z naught is the star center of D. And the integral is taken along some path in D from z naught to z, which you know exists because it's star-shaped, right? Now, how do you prove that? Well, the proof is essentially just that I honestly think we've already proved this in some sense or another in chapter 3, if you really just sort through it. But if I want to show that, if I can show that if f of w dw is a closed form, then that would imply this result, right? Because closed implies path independent on a star-shaped domain, and we actually worked this formula out on the closed space, closed set. So why is f of w dw closed? Well, if it's holomorphic, that implies that it's closed, right? We proved that before. That's the proof. Hey, let's look at a different example, yeah? Now there's not time to project. That's fine. I wanted to get the Cauchy's theorem today, but I'm going to instead just end class with an interesting example, okay? So let's see here. What if we wanted to look at the integral of dz over z, right? And what we're going to do is we're going to do it over this thing. So it's almost a circle. All right, and then so like we'll basically do it for z equals to e to the it for minus pi plus epsilon less than or equal to t less than or equal to pi minus epsilon. So I'm almost getting to the slit, but not quite. All right, if I do that, is this function integrable? on this curve. Well, yeah, that curve, it has no problem. The slit is not there. In fact, this curve is in a star-shaped domain on which the given function is holomorphic, right? F of z equals to 1 over z is an element of the holomorphic functions on the slit complex plane. And straight up, this is the log, right? Log of z, evaluated from where to where? Yeah, e to the I pi, let's see, where do we, which direction am I going? Counterclockwise, right? So like this. So I start at e to the epsilon minus pi, I guess I could say. And I go up here to e to the I, what? Pi minus epsilon, right? So what do we have? We've got log of e to the I pi minus epsilon minus the log of e to the I epsilon minus pi. So what's this and what's this?
I psi minus epsilon
Mm-hmm.
minus I epsilon minus pi.
Right, which we could rewrite as what? That's 2 pi I minus 2 I epsilon.
So then the integral only has an imaginary part. Its real part is equal to 0.
Indeed, yes, that is true.
That's interesting. Can you draw something about that?
Michael, what are you saying?
I know, right?
Well, I don't know, can I draw something about it? This is a complex linear combination of two real integrals. There's two line integrals of two force fields here, for what it's worth.
Okay.
But do you see what happens? As epsilon goes to 0, what happens? Look at this example, see?
It goes to 2 pi I.
Epsilon 0, this goes to 2 pi I.
Oh.
By the way, this isn't the first time I showed you guys this example. You should be able to see through this. What's 1 over z, dz? It's dx plus I dy over x plus iy. What is that? Multiply this by x minus iy over x minus iy. You'll find out I'm really a creature with very limited imagination, because what you're looking at is x dx plus y dy plus I times x dy minus y dx, all divided by x squared plus y squared. The imaginary piece of this is the form I pointed out to you was closed but not exact on the unit circle. This is the same example I showed you before. So what you guys doing for break?